All right, welcome to Dynamics. We're in chapter 13 now, where things start to get really interesting. Pretty exciting what we can do when we start applying Newton's second law to what we've done so far in dynamics. And so we've got his second law telling us force equals mass times acceleration. And up to this point, we've dealt with calculating that acceleration in several different coordinate systems. And so if we're able to say, well, it's got a certain acceleration and a certain mass, then we could figure out what force is involved with that motion, right? Or what force would be required to cause that acceleration more specifically, right? Um, so the motion of an object depends on the forces acting on it. So the acceleration, for example, of this parachuting person, they've got a drag force going upwards and they've got their own weight force going downwards. And so their acceleration would be a combination of, right, what forces are acting on them and what is their mass. We could figure out what their acceleration is. So if we knew the net force, then yeah, we could find its acceleration. If that was a constant acceleration, which probably a drag force is going to be a constant force as well as gravity, right? Both acting constantly, we should have a constant acceleration, and we could figure out what their velocity is at any point in time. Here's another example of something that we might know, we might want to know, right? What the acceleration of the truck is based on what kind of mass he's towing. What's the force between them, right? If you're designing the pin that hooks together these different carts or something like that. Here's another example. We could do our pulley games that we've done before and figure out what the acceleration of the box is, right? We've done that before. And if we can find out what that acceleration is, um, we can then, size the mass, or we could use, this would be more likely, we'd have some known mass that we want our elevator to lift. We know we want it to move at a certain acceleration, therefore, what force should be applied, and we can do that and size a motor that can provide the right amount of force to lift, right? So we could figure out what that tension in the cable is, something like that. You could size the cable as well. So this all comes down to Newton's laws, which reviewing, right? We have the first one, an object that at rest stays at rest, or an object in motion stays in motion until acted on by unbalanced forces. Second law is if it's not balanced, right? If the forces are not summing to zero, then there'll be an acceleration in the direction of the imbalance, right? Proportional to its mass. And then the third law, equal and opposite reaction, that kind of spelled out all of statics for us between those three. So we're going to really focus on the second law, which is where we get this force equals mass times acceleration, right? The acceleration is proportional to the net force of unbalanced force acting on the object, right? So very powerful equation. So far, we've just used that to find weights for the most part, right? But now we've come up with acceleration in all our different systems that we've been playing with in chapter 12, and we will be able to calculate the force caused by that acceleration, or vice versa, right? What is the acceleration caused by a force? And so that's going to be the next step here. That'll be a really powerful tool in coming up with unknown accelerations or unknown forces on a particle. So, yeah, I guess we need this caveat. You can't use F equals ma when you approach the speed of light, or if you have a tiny, tiny mass, right? Things get weird when you get into those extremes. But for all our intents and purposes, we will have Newton's second law be very applicable and accurate to what we need to do. So this was a cool video for those watching online. I'll let you see that. so I don't get copyright issues for recording the video. So go into the slides, hit that link, and watch that video. It's kind of a neat one of astronauts going and playing with Newton's second law in the International Space Station. So here we're going to need to get back familiar with our units if we aren't already. Hopefully you remember the mass mess of the US system, right? Because we've got kilograms, which is nice, for mass in the SI system. So if we want to get a weight in the SI units, we just did a mass times gravity, right? But that won't just be for weight now. Anytime that we have an acceleration, we could just do kilograms times meters per second squared, and that'll end us up in units of newtons. And there's our gravitational constant that we've used many a time, right, for Earth. Now, for the US system, we've got now um, weight being more of a derived unit rather than that's the preferred unit, right? It's pounds. We don't use slugs that much, but that is the equivalent of the kilogram. So if we need to come up with a mass, we'll have to take the pounds and divide it by gravity, right? If the weight is in pounds, that would equal mass times acceleration. And that acceleration would be 32.2 feet per second squared, and the mass would be in slugs, right? So anytime you divide a pound by 30 by feet per second squared, you end up with slugs. Okay? So that's good to keep in mind. That's definitely going to come to play in the rest of this class. Anytime we need the mass for an object that is given to us in pounds, we'll want to do it in slugs. So both of those numbers, by the way, the 9.81 meters per second squared and the 32.2 feet per second squared, gravitational constants for Earth are definitely good ones to put on your cheat sheet or just lock away in there forever because you'll use them for this class and many others.